In this video, we'll continue our study of hypothesis testing, this time using it to test claims about means. Pop quiz. What's the average human body temperature? If you're like most people, you said 98.6 degrees Fahrenheit, or 37 degrees Celsius if you use the metric system. That's what everybody always says. It's common wisdom at this point. But have you ever wondered where that number came from? Turns out we have that number because of Karl Wunderlich, a German physician, who got that number from experimentation in 1868. It kind of makes you wonder, medicine's come a long way since 1868. Is Wunderlich's number really accurate? Or might we get a different number with modern technologies and techniques? We can find out with, you guessed it, a hypothesis test. The thing we want to test is the mean body temperature in degrees Fahrenheit. We label that as mu, since it's the mean body temperature for the whole population. Our null hypothesis is that conventional wisdom is right, and Wunderlich's measurement of 98.6 is correct. What about the alternative hypothesis? Well, we really don't have a hunch on whether it might be higher or lower. So the most appropriate hypothesis is that the mean temperature is just not equal to 98.6. It remains to be seen which direction it might be off in, if at all. This time, just to be a little different, we'll use 1% as our significance level. That's setting a higher standard for rejection. We're only going to reject the null hypothesis if it would mean that a result is so rare that it would happen less than 1% of the time. Okay, now we need some data. I found some data on rdrr.io, which is a website with lots of documentation about R. What's R, you ask? It's a software environment that specializes in statistics, both doing computations and displaying the data. It's very powerful, and it's also free. So if you plan on going further into statistics, chances are you'll learn to use R at some point, and you won't regret it. Anyway, here's the data set. It's actually given as a stem plot. Remember those? With a sample of 25 temperature measurements ranging from 97.4 degrees Fahrenheit to 100 degrees Fahrenheit. With a little work, we can find that the sample mean is 98.524 degrees Fahrenheit, and the sample standard deviation is about 0.678 degrees Fahrenheit. Now, can we use this data to perform a hypothesis test? Let's check our conditions. First of all, the website says the sample was random, and we can assume these measurements are independent. That's what the less than 10% of the population requirement is really all about, making sure the observations are independent, or at least close enough. We also have some additional conditions we need to look at based on which kind of test we'll be using. Remember, if we know the population standard deviation, sigma, then we can use a z-test. But we only know the sample standard deviation, so we have to use a t-test instead. Either test can be used when the population parameter is known to be normally distributed, or when the sample size is large enough, at least 30. Unfortunately, we don't have either of those conditions. But we're in luck. It turns out the t-test is robust enough that it still works for smaller sample sizes as long as the data is approximately normal, symmetric or at least close to it, and unimodal, having only one hump, with no outliers. And if we plot our data in a histogram, remember those? Then we see that's the case. So we're good to go ahead and continue with our hypothesis test. Now let's put our sample in context. If the null hypothesis is really true, that is, if the mean body temperature is 98.6 degrees, then the mean of the sample means will be 98.6 as well. As for the standard deviation of the sample means, the standard error, normally it would be sigma over root n. But once again, we don't have sigma. That's okay though. We can get close enough by using the sample standard deviation, s, and dividing it by the square root of the sample size, n. That gives us about 0.1358. If we were using a z-test, we could just go ahead and use sigma over root n. But in a t-test, we have to use S over root n instead. From there, our test statistic is once again calculated just like a z-score, except since we're using the sample standard deviation, it's not really a z-score, but a t-score. The idea is still the same though. Take our sample mean, 98.524, subtract the hypothesized population mean of 98.6, and divide by our approximate standard error, 0.1358. That gives us a t-score of about negative 0.56. Okay, now we need to use that test statistic to find our p-value. Since our null hypothesis is just that the population mean is not equal to 98.6, but we don't have a hunch as to whether it's greater than or less than 98.6, we're using a two-tailed test. We're going to find the probability that we get a result that's off by as much as ours was, but in either direction. So that's the probability that t is less than negative 0.56, or t is greater than positive 0.56. Excel has a nice built-in function to handle two-tailed t-tests, t.dist.2t. Just make sure you put a positive number for the test statistic, otherwise it'll give you an error. And don't forget the degrees of freedom, which is your sample size 25 minus 1. So when we do the calculation, we get about 0.58. That means that a result like ours would happen by pure chance about 58% of the time, more often than not. Remember, our significance level alpha is 1%, and our p-value is much greater than that. So we fail to reject the null hypothesis after all. Our results are nowhere near rare enough to justify doing so. Put in context, we'd say that there's insufficient evidence to conclude that the mean body temperature is not equal to 98.6 degrees Fahrenheit. Be careful though. Remember, that does not mean we accept the null hypothesis. We haven't proven that the mean body temperature is 98.6 degrees Fahrenheit. And it turns out there's actually more to the story here. In 2019, a paper was published that collected body temperature measurements from 36 separate studies, which altogether gave a sample of over 9,000 measurements. Altogether, when converted from Celsius to Fahrenheit, those measurements had a mean temperature of 97.862 degrees Fahrenheit and a standard deviation of about 0.774 degrees Fahrenheit. I'll let you work out the details on your own. It's good practice. But the test statistic ended up being about negative 9.43. And that works out to a p-value of roughly, get this, 5 times 10 to the negative 21st power. That's a decimal point, 20 zeros, and then a 5. That is ridiculously small. And so even with an alpha of 0.01, that's pretty convincing evidence that the mean body temperature isn't really 98.6. That's the power of having a large sample size. And by the way, keep in mind that's still just an average. It differs from person to person. Also, your body temperature actually varies throughout the day, and depending on what part of your body you use to take your temperature measurement, you can actually get different results. It's a random variable, just like anything else.